Have you ever felt it? That moment when the ground moves under your feet? It's one of the most powerful and, let's be honest, one of the most terrifying experiences you can have. Today, we're going to strip away some of that fear and just dive right into the science, the history, and, the myths behind that shake. Just think about that for a second. The world was breaking into pieces. That comes from someone who survived the biggest earthquake ever recorded, and it just perfectly captures that raw feeling, doesn't it? It's not just a tremor. It feels like the one thing we count on to be solid is just falling apart. And that's why our brains almost never jump to earthquake right away. You know, when a tremor hit Bangkok not too long ago, people's first thoughts were just all over the map. Some folks thought they were having a dizzy spell. Others, who were just standing still, actually worried they were having a stroke. There was even one guy in a car who turned to his friend and asked if he was testing the shocks. Our minds will literally grasp for any other explanation, because the ground moving, that just feels impossible. So, here's our roadmap. We're going to start with that strange, disorienting feeling. Then we'll get into the science and figure out how we actually measure these things. From there, we'll play detective and solve a 300-year-old mystery. Then we'll bust some of the biggest myths out there. And finally, we'll ask the most important question. Are we ready for the next big one?
All right, first up, when the ground shakes. That universal feeling of disorientation. Let's get into what is actually physically happening.
Okay, the simplest way to think about it is this. Picture the Earth as a giant ball of super hot lava. Now, floating on top of all that liquid rock is a thin, brittle crust. And it's broken up into these massive pieces, kind of like crackers floating on soup. These crackers are the tectonic plates, and they are always moving, grinding past each other, sliding under one another. Every now and then, they get stuck. The pressure builds and builds and builds until, snap, they suddenly break free. That incredible release of energy, that's the shake we feel.
Section 2. Magnitude versus Richter. You hear these terms thrown around every time there's a quake, but what do they really mean? Let's break down the science of the shake and clear this up for good.
So to measure a quake, you need a seismograph, and the original design is just brilliantly simple. You might think it's the pen that's shaking, right? Nope, it's the other way around. The pen, thanks to good old inertia, stays perfectly still, while the roll of paper, which is attached to the ground, shakes like crazy underneath it. It literally draws a picture of the earthquake. Now here's the crucial thing to get. Richter and magnitude, they're scales, not units. You don't say 5 units Richter. For a long time, the Richter scale was the standard, but scientists realized it wasn't very accurate for the really big quakes, anything over a 7.0. So they came up with a much better system called the moment magnitude scale. That's the one we use today. So when you hear on the news a magnitude 8.2 earthquake, they're talking about moment magnitude.
And that brings us to another key difference, the quake's energy versus its intensity. See, an earthquake has only one magnitude. That's a single number that represents its total power right at the source. But the intensity, the shaking that you actually feel, can be totally different from place to place. So you could have a magnitude 8.0 quake, but in one city it might feel like a destructive level 9, while 100 miles away it's just a gentle level 2.
Okay, section 3. Now let's put this science to work. We're about to become historical detectives and solve a 300-year-old mystery, a giant earthquake that happened long before we had any instruments to record it, but left clues all across the Pacific Ocean. Okay, check this out. Along the coast of Washington State in the US, there are these creepy ghost forests, stands of dead cedar trees. For hundreds of years, nobody knew why they all died at the same time. The first big clue? Looking at tree rings in geology, scientists figured out the land had suddenly dropped by 6 feet, flooding all those forests with salt water. But the final piece of the puzzle came from halfway across the world in Japan. They had these ancient records describing an orphan tsunami, a massive wave that hit their coast on January 27, 1700, with no earthquake to warn them. Scientists put the two mysteries together, and it was a perfect match. The quake in America was so big it sent a tsunami all the way to Japan. They even figured out the exact date and time. A ghost quake solved by science. Incredible. This brings us to one of the most stubborn beliefs about earthquakes, that animals have some kind of sixth sense. We've all heard the stories, right? Oarfish washing up on the beach, dogs barking like crazy just before a big one hits. But what's the real story?
Well, the scientific consensus is pretty clear. There's just no proof that animals can predict quakes hours or days ahead of time. The whole oarfish thing, it's a classic case of what we call cherry picking. We remember the one time an oarfish washed up before a quake, but we forget the dozens of times they washed up and nothing happened. What's really going on is likely this. Earthquakes send out 2 waves. a fast, weak one called a P wave, then a slower, stronger, more destructive one called an S wave. Humans only feel the S wave, but some animals might be sensitive enough to feel that first P wave just seconds before we feel the shaking. So they aren't predicting anything, they're just reacting a few seconds before we do.
So, last section. Are we ready? We know we can't predict them, but we can prepare. And the first step is really understanding the incredible scale of the threat. Let's see how some of history's biggest quakes stack up.
Okay, just look at this. The horrifying Tangshan quake in 1976 was a 7.8. Then you have something like the potential Nankai Trough quake in Japan, which scientists think could be a 9.0 or even bigger. But then, look at the 1960 Chile earthquake, a 9.5. That is the largest ever recorded. The jump in energy from a 7.5 to a 9.5 isn't just double, it's over 1,000 times more powerful. That level of energy is just almost impossible to imagine.
And to put that power into a picture you can imagine, that 1960 Chile quake created a tsunami that hit the coast at 25 meters high. That is an 8-story building. Just try to picture that. A wall of water as tall as an 8-story building moving at the speed of a jetliner.
So since we can't stop the Earth, our only real defense is good engineering. But a building is only as strong as its weakest link. It all has to work together. You need modern design codes, you need quality construction, you need to use the right materials, and you have to do proper maintenance. If any single one of those things fails, if a contractor cheapens out on the concrete or a building isn't maintained, the whole thing is at risk.
So what should you do when it happens? The procedure is actually very simple. First, stay as calm as you can. Your gut instinct is probably going to be to run outside, but that's often the absolute most dangerous thing you can do because of fallen glass and debris from buildings. Instead, you do this. Drop, cover, and hold on. Drop to the ground, get under a strong table or desk, and hold on to it until the shaking is completely over.
So here we are. We understand the science. We've learned from the history. We even have the engineering know-how to build cities that can withstand these events. The science is clear, and the past is a pretty stark warning. So really the only question left, for governments, for communities, for all of us, is will we actually be ready for the next one?